Hi, welcome. This is, the objective of this particular talk is to discuss couple of methods through which we can solve multivariable utility maximization problem, in a simpler way. Uh, uh, so so basically, we'll be learning how to solve utility maximization problem. It's a standard utility maximization problem involving three or more goods. Okay. So even though I'll be using utility maximization problem here, but the kind of methods that I'm going to describe, they can be used in alternative problems as well. Let's say if you want to solve a cost minimization problem, or you want to solve any other optimization problem involving several variables, it can be used. These kind of methodologies that I'll be discussing in this particular seminar can be used in those situations as well. Okay. uh, so so what I'll do is I'll do an example, to demonstrate the methodology. And of course you can just change the problem and apply the same methodology and solve a different problem as well, using this methodology. The idea of the seminar is to convey the methodology. Okay. And it's actually very nice methodology because the idea is kind of straightforward, and it's pretty simple, and it's just going to use your understanding of how to solve two variable optimization problems, to actually solve multivariable optimization problems. Okay. And it's a very neat way of of reducing the problem. Let's say if it involves three or more goods, how can you actually reduce it to a problem involving two goods or maybe two variables? Okay. And maybe you'll have to solve it multiple times, but you can actually just reduce the problem of solving utility maximization problem involving three or more goods to solving multiple two variable optimization problems. And the convenience that we get with two variable optimization problems is that you can actually use graphs, and you can use your experience. You must have seen lots of two variable optimization problems, so you can actually use multiple there are multiple ways in which you can approach and solve them. So you can actually use any combination of those techniques uh, to solve two variable optimization problems. Okay. So here is the optimization problem that I'll be solving. Okay. So suppose you want to maximize the utility, which is a function of four variables. Let's say, this is the utility function 2 root xy, okay, plus min wz. Okay. So these are four variables that you are choosing. Okay. And you want to choose x, y, w, z so that you maximize this utility. Okay. Subject to the budget constraint, which is pxx plus pyy plus pww plus pzz less than or equal to m. Okay. Where these prices are given. Okay. So px is given, py is given, okay, pw is given, and pz is given. Okay. And income is also given. So you want to solve this problem. Okay. And one way in which you can approach and solve this particular problem is the following. okay, that you can actually consider this procedure, okay, that, okay, fine, you can just basically divide this procedure into two steps. Okay, step one is allocate the total income M, okay, so allocate out of the total income M, MXY, the amount MXY for X and Y, okay, and the remaining amount MWZ for W and Z, okay. So you can allocate the total amount of M to MX to X and Y. Basically, out of it you can allocate MXY for XY and MWZ for W and Z, okay. And then in step two, okay, what you do is basically you can call this stage one if you wish. In stage one you allocate the income, okay, and in stage two, what you do is you spend the amount allocated to XY and WZ respectively on XY and WZ in the best possible manner, okay. So spend MXY on XY and MWZ on W and Z in the best possible manner, okay. And then once you actually solve this stage two problem, okay, then go back and solve stage one problem. It's just like backward induction, okay. Then solve stage one problem, that, okay, fine, if you actually spend MXY on XY in this way, MWZ on WZ in this way, then how much should you allocate to XY and how much you should allocate to MWZ, given that your objective is now a function of MXY and MWZ. So basically, when you actually solve the stage one problem, what will happen is that that this particular problem, will become a problem of just two variables, MXY and MWZ, okay. And we'll see how, okay. And then of course, it's just a simple two variable optimization problem that you can easily solve, okay. So let me tell you exactly what's going on over here. So let's solve stage two problem first. Stage two is basically when you have already allocated MXY to XY and you have already allocated MWZ to W and Z, okay. Then as a rational consumer whose objective is to maximize this sum, what will you do? How will you actually spend MXY on XY? Notice that this is the component of the utility function which is affected by XY. So what you'll do is, in stage two, you are in stage two first. So basically you're going to solve it by backward induction. So first you're going to maximize with respect to XY, okay, in R2 plus, okay, 2 root XY, okay. And what you'll do is, whatever amount that you have allocated to X and Y, you spend on X and Y in the best possible manner, okay. You spend this amount on X and Y in the best possible manner, and the amount that you have allocated to W and Z, you spend that amount on W and Z in the best possible manner, okay. And then when you solve these two problems, this solution to this problem will depend on only MXY and PX and PY, and therefore the objective will only depend on MXY and PX and PY. Here also the objective will only depend on when you actually find the solution, and you plug in the solution in the objective will only depend on MWZ and PW and PZ, okay. Then what you do is, you maximize that with respect to how much amount you should allocate. Okay, subject to, okay, and that's it. This is a simple procedure, to solve this four variable optimization problem in of a consumer. Okay, so let's solve it. Okay, let's just do this. Okay, so let me first solve this problem. Okay, and this is easy, right? I mean, you already know how to solve a two variable optimization problem, so you can easily solve this problem. Okay, so so what are we going to get? If you just solve this problem, let's call it problem 1. Okay, let's call this problem 2. Okay, let's solve problem 1. So solution to problem 1 is x, y, and let's call these intermediate solutions. So these are intermediate solutions because these are not the final solutions. Okay, x I y I is equal to, okay, so mxy by 2px. All of you know how to get this, right? So I'm assuming that you know how to solve this problem. Okay, is that okay? Do you all agree this is what we're going to get? Yes. Okay, so now you can now you can solve the second problem. Okay, so second problem is your intermediate solution in case of the second problem is wizi equals mwz pw plus pz, okay, comma mwz pw plus pz. Is that okay? Fine. Are all of you convinced that this is what you're going to get if you're going to solve this? Okay. Okay, so once you have this, then you can substitute this over here and substitute this over here and rewrite the stage 1 problem. Okay, so remember, it's a stage 1 problem, which is the allocation problem, which is maximizing this plus this subject to this constraint. So you can just write the stage 1 problem in this manner, which is maximize with respect to mxy mwz, okay, in R2 plus. Okay, so what is 2 root xy? So if you take root of this into root of this, multiply them, okay, and it will be mxy divided by root pxpy, right? That's what you're gonna get. Yes or no? Because 2 root xy, so 2 will cancel the 2 in the denominator, okay, and square root of mxy into square root of mxy will be mxy. Okay, so this will be the product of these two, and then taking the square root of it and multiplying it by 2. And what is min wz? Since this is same as this, this is same as this, so min wz is actually this only. So you can just write plus m wz upon pw plus pz. Okay, and what is your constraint? Your constraint is mxy plus mwz is less than or equal to m. Okay, so this is notice that now again it's a two variable problem, because you're just choosing these two and these are given, so these are like constants. Okay, and you're just simply solving this two variable optimization problem where objective is linear in mxy and mwz, and this is your constraint. Okay, so this is again straightforward. You can actually solve for mxy and mwz now. Okay, so what is mxy? And what is MWZ? Let's solve it. Okay. So notice that the solution is, so of course, it depends on whether this is smaller or this is smaller. So if root pxy, if root pxpy is smaller than pw plus pz, then in that case mxy will be m, right? In that case, you would like to, because it's a linear objective, so whichever coefficient is bigger, you will put the entire income there, right? So if root pxpy is less than pw plus pz, then this coefficient is bigger than this coefficient. Coefficient of mxy is bigger than coefficient of mwz. So you're going to put your entire income on mxy. So it will be m comma 0. Okay, right? Okay, and if root pxpy is bigger than pw plus pz, okay, then in that case, it's just the opposite, which is 0 comma m. Okay, and if root pxpy is equal to pw plus pz, then there are a set of solutions in this case, which is basically, you can actually choose anything on this line, so you can choose to spend it in any way, so in that case, there are multiple solutions. So you can say that, theta m comma 1 minus theta m, where theta is in 0, 1. So you can choose to put any proportion of income on mxy and the remaining on mwz. Okay, so anything is okay, because it's just the objective, the indifference curve of the objective will coincide with the boundary of this constraint. Okay, and therefore, this is how you can just write the solution. And now, once you know that how you're going to allocate your income in these cases, then you can go to your step 2 solutions and plug in place of mxy and mwz, the m or 0 or whatever it is, according to these situations. So basically you can rewrite the solution in this manner. Okay, so let me just erase the step 2 from here and write the solution. Okay, so basically what you're going to get is as follows: x d y d w d z d, and it's a function of px, py, pw, pz, and m. Okay, and it is as follows. Okay, so okay, so if root px py is less than pw plus pz, okay, then in that case, you are going to allocate m to mxy and 0 to mwz, which means that you are going to consume, according to this, m by 2px comma m by 2py comma 0 comma 0. Okay, and let me do one thing. Let me just write it as set of solutions, because there is this case where there are multiple solutions. So let me just write it as a set of solutions. Okay, and if root pxpy is greater than pw plus pz, in that case, the solution will be 0, 0, m by pw plus pz, comma m by pw plus pz. Okay, and if root px py is equal to pw plus pz, then in that case, there are multiple possibilities. So what you can do is you can write it in this manner, that it is, so just put theta m here. Okay, so it's theta m by 2px, comma theta m by 2py, comma 1 minus theta m by pw plus pz, comma 1 minus theta m by pw plus pz. Okay, where theta is from 0, 1, close interval, and that's it. This is the demand. Is that clear? Okay, so this is actually kind of a nice way to, as I've said, the thing is that you are solving two variable optimization problem 3 times. Okay, first you have solved a two variable optimization problem in stage 2, which is this one, and then this one, and then the overall, which is basically this one, and then just simply combining it and writing the solution in terms of px, py, pw, pz, and m. That's all that you're doing. Okay, and it's a nice trick. Okay,